Hi guys, this is Yifan from Zhejiang University, and here I would like to introduce our work which measures the intersections between large language models and the cryptographic API misuse detection. So let's start with some brief introduction. In real world, the developer should confirm the production is secure, and as a result, a series of cryptography-related operations is needed, such as encryption, message digits, and so on. The developer could hardly implement all these functionalities themselves. So most of the mainstream platforms provide architectures to support this process. For Java, there is standard architectures, GCA, and for other languages, there are also third-party libraries. However, even though the architectures are well established, the large number of such APIs still pose a challenge for developers to use them. And even worse, each class of cryptographic APIs often follows various implementation standards, and a single misconfiguration of the parameters could lead to the downgradation of system security level. And we could see that there are a lot of cryptography-related CWEs. So such misuse is dangerous, and many works propose some techniques to solve the detection of such misuse. And most of these tools focus on the Java ecosystems, and existing sort of works are mostly pattern-based techniques, which rely on the expert-written rule sets for a set of detection. However, as we all know, the detection of pattern-based techniques rely on its rule sets, and the real-world scenario is complicated. And study already show that even the source detectors suffer from severe false positive and false negative cases. In terms of false negatives, a static rule set can easily miss real-world misuse that fall outside the predefined patterns. Let's see an example. In real-world practice, the developers often customize parts of their functions instead of following the standard call chains. In this example, the official documentation may ask the developer to use a key specification object for key generation. And then the detector designer focus on this specific API and craft a set of rules to detect the misuse of it. However, we find that in real world, there is a case that the developer implements a long-standard key derubbing methods. And in this call chain, it does not use the expected API. Then this key derubbing process uses only a single round of hash, which should be at least 10,000 rounds to resist attacks. Such kinds of partial customization completely evades all pattern-based techniques. So how about report all such long-standard operations as misuse? There are also studies show that some of such rigid rules can lead to more than 90% of the alerts to be false positive. And actually, an operation's security may vary depending on the context. And most pattern-based techniques regard all the use of non-security random number generator as misuse. And this causes high false positive, since non-security random number generator could also be used for some security insensitive scenarios. And similarly, some pattern-based techniques consist the outdated algorithm as insecure. However, such weak algorithm could also be the foundation for implement such some advanced encryption mode. So if the detector reports too many false alarms, the developer will never use it. So now we have LLMs. The emergence of large language models provides a new chance to complement these limitations. And LLMs are known for their code comprehension and might analyze the related context to filter some false positive, and also may have the potential to locate a customized part according to the correlation. And then you could find a hidden misuse. It sounds so fancy, but is that the whole story? Maybe not. Large language models could also generate unreliable results. This is a critical flaw for security analysis. For an encryption code, it may generate contradictory reports during multiple response. One said this is okay, and one said there is a misuse, and we don't know which one we should believe. And it could also generate factual errors which entirely misunderstand the semantics of the code targets. And even worse, automated oracles are not available for this task. For some software engineering tasks, such as program repair, you could use the unit test to do some pre-evaluation, but the correctness of a security report necessitates the human evaluation in this process. So in this work, we aim to quantify the effectiveness of LLM-based cryptographic misuse detection with a specific focus on where LLMs can complement traditional detection methods and what's their weakness for this task. And this is our evaluation framework. For the benchmarks, we incorporate two kinds of benchmarks. One is the manually crafted benchmarks from handcrafted samples and the synthesis samples. And another benchmark is the real-world benchmark, comes from the Apache Java projects. And for the LLMs, we evaluate both the commercial LLMs and the open source LLMs by the time the research is conducted. And it's worth noting that most of our findings are still replicable in the most recent GPT-4o and Gemini 2.5 Pro. And for the detection settings, we prompt LLM's capability with two distinct settings to mirror traditional detection. And one is unconstrained detection, where we do not restrict LLM detection scope, allowing themselves to determine the target categories. This means that all crypto-related CWEs may be considered as potential targets. And conversely, we provide a detailed description of 6 high-impact groups. And as we previously mentioned, the mitigation of low-quality misuse report is critical. And this work will also propose some simple while effective methods for that. For the same test case, we launched multiple detection queries concurrently, and this compiles a response set and increases the statistical likelihood of detecting the misuse. However, the expanded response could also increase the false positive alerts. And here our insight is that the distribution of misuse across multiple responses can reflect LLM's confidence towards specific misuse. This is maybe now called self-validation strategies in some similar works. And we designed the validation query, which re-evaluates the targets with previously generated report. And finally, we calculate the metrics based on the original ground truth. And meanwhile, when an unknown misuse is reported, we separately assess its correctness. And only a report with both correct locations and the root causes is regarded as a true positive alert. So let's see the first research question. We explore the effectiveness of large language models detection. We could see that large language models could achieve at most 90% recall for this task, and the detection results vary significantly depending on the detection settings. And from here, we could see that the original detection precision could be quite low, and even for advanced LLMs like GPT-4, the recall could be less than 0.5. The precision issue is more pronounced for unconstrained settings. So when LLMs target small categories of misuse, simply relying on the model knowledge could be wrong. And for instance, it may require a padding algorithm for strip cipher, which is totally wrong. And conversely, the task-aware setting could enable LLMs to generate more true positive alerts. This result indicates that from the model performance perspective, it's better to define a focused detection scope. And we then investigate the false positive alerts. And we find that one major source of this is that LLMs can be misled by unrealistic cryptographic context, often found in the manually crafted benchmarks. And here is a test case which is designed to evaluate whether the model could detect an outdated digits algorithm, MD4. So for some models directly report that MD4 is an outdated algorithm, and this matches the ground truth. And however, advanced models may notice more context, like method names, and then extend their analysis. And in this case, GPT-4 noticed the method was named encrypt and mistakenly recommend adding a salt for it. However, as this case does not have a complete logic, we know that this is a handcrafted test case. So this report is unnecessary. We could see that while advanced LLMs try to reason over the broader code context, the benchmark often ignores the full structures and intent of the surrounding code, and this leads to the unexpected report. This issue is not real. We find that over 60% of the test case we examined in the past works could contain flawed or unrealistic code context, and such samples could include direct misuse introduced by the benchmark developers. Then this shows that even the professional developers could also make mistakes. And we also find some impractical operations that should not happen in real-world development. And in many cases, the code is functional valid, but it operates at a lower security level and should be enhanced. And this result shows that the flaws of existing benchmarks, when they suit pattern-based detectors, they might not fully capture the capabilities of LLMs due to their context insensitivity. And due to these influences, the original report of LLMs involves two main categories of errors. And the first category is from the misinterpretation of code semantics. LLMs may either misunderstand the intent of the code or the role of some local variables. And in these examples, LLMs treat a cipher name as a password, and then it reports a false positive alert. The second type stems from incorrect knowledge of the cryptographic APIs, where LLMs could mistakenly flag a circular API as vulnerable, and this leads to the false positive. And fortunately, the validation strategy could effectively correct false alerts. So for the real-world targets, LLMs could generate more precise results, but as the target size increases, LLMs could be misused when the size reaches the context window of such large language models. And we could see that the recall drops sharply when the file size increases. And there are also some special cases when LLMs actively ignore some misuse. For example, in this case, the LLMs notice the ground truth misuse as acceptable because a notation referred to a corporate coding practice from another project. Then it tolerates some use of outdated algorithm. So understanding large language models detecting effectiveness, we then compare them with stochastic detectors. And we could see that open source LLMs could already perform competitively to the SOTA detectors on our benchmarks. And for the ground truth misuse in real-world benchmarks, LLMs identify 17 unique cases where the previous traditional detectors could not find. And GPT-4 identifies 5 previously unknown misuse beyond the ground truth. And LLMs could also miss some multi-hop call chains, which involves multiple functions in a long call chain. We summarize large language models' advanced capabilities to uncover these known misuse cases. First, LLMs could extend high-level descriptions into a variety of scenarios. And this broader and more flexible rule sets surpass pattern-based detectors. And this capability contributes to identifying of 12 additional misuse cases. And LLM also performs some capabilities to do generic value resolutions, and it helps to identify the outcome of some logic conditions, and something like string manipulations result. And by focus on the detection of security-related context, LLMs are able to eliminate all false positive alerts in security-insensitive contexts. And despite of the advantages, we also identify some recurrent failing patterns, illustrate current LLM's blind spots. And remarkably, in 41.3% of cases, the error was due to the incorrect cryptographic knowledge. Interestingly, we find that LLMs from different vendors may generate the common types of cryptographic knowledge misunderstanding. And this suggesting a fundamental flaw maybe in the current training set of the large language models. And in over 50% of the cases, the false analysis was caused by large language models' misunderstanding of code semantics. We also classify these cases into 5 distinct categories. And please refer to our paper for more details. And And for large inputs, open source models could generate totally nonsensical response. And this contributed to a small portion of the hallucinations result. And finally, we conducted a multilingual study across top Java and Python repositories on GitHub. We used optimized settings according to previous findings and interact with the maintainers of these repositories, maintainers for confirmation. We could see that the acceptance rates of LLMs reported misuse are much higher than traditional detectors. And we also find some interesting results in some case study. And we concluded the reasons why the developer of the popular repository maintainers misuse the cryptographic APIs. And one reason is standard involving. In a widely started project, the maintainer updated the TLS protocol in 2019, and 2 years later, TLS v1 was also deprecated. And this rendering the update insufficient, and the maintainers ignored it. And the second reason is most of the developers could mimic the upstream project. And we found a special case when we interact with the developer. They said that they thought it was a valid operation, since the OpenSSH also used it. However, we find that it is weird that NIST forbade it, but OpenSSH still used the old algorithms and didn't update along with it. And most of the developers could consider the compatibility issues when they update an outdated algorithm, and the downstream developers could be affected by it. And one Apache project's maintainer told us that they attempt to optimize the logic according to our suggestions, but then they temporarily reverted the changes due to the user compatibility requirements. And for more discussion, please check our paper. So that's all. For conclusion, we find that large language models could complement traditional cryptographic detectors in detecting misuse in customized functions and the context-related security or insecurity operations. And the recurring failure patterns show that LLMs could weakness and emphasize the necessity of reliable validation techniques and cooperation with static detectors. And for future works, we may keep going on eliminating the unrealistic code context from existing benchmarks and refine LLM's training data to reduce false cryptical knowledge. Yeah, that's all. Thank you.